Welcome back for another deep dive. We've got a really fascinating paper to explore today. It's all about how we can bring the power of graph neural networks to the world of wireless communication.
Yeah, this paper's tackling a really significant challenge, making graph neural networks, or GNNs, work effectively in these real-world wireless settings, where you've got all these messy things happening like fading signals and interference.
Right, and not exactly the ideal, pristine environment that a lot of machine learning models are trained on.
Yeah.
So for our listeners who might not be as familiar with GNNs, and I'm guessing that includes a lot of you working with wireless networks and signal processing who are coming from more of a traditional machine learning background.
Yeah.
Could you give us like a quick rundown of what GNNs are and why they're so powerful?
Absolutely. So in a nutshell, GNNs are a type of neural network that's specifically designed to process data that has this graph structure. Think about things like social networks, transportation systems, or even the structure of molecules.
Oh, interesting.
All of these are examples of systems that can be represented as graphs with nodes and edges and GNNs. They really excel at capturing these relationships between these nodes and then using that information to make predictions or classifications.
Okay, that makes sense. So you've got these GNNs that are great at understanding relationships within these complex networks, but then you bring in the real-world messiness of wireless communication. What happens when you try to bring those two worlds together?
Well, that's where the problems start to arise. Traditional GNNs, they often assume these perfect communication links,
Right.
ignoring the realities of fading and noise. And as anyone who's ever, struggled with a dropped call or a slow internet connection knows,
Oh, yeah.
these impairments, they can really significantly impact performance.
For sure. So how does this paper propose to bridge that gap? What's the secret sauce?
Well, the researchers introduced this really novel approach that they call AirGNNs. And essentially what they do is they integrate a technique called over-the-air computation, or AirComp, directly into the GNN architecture.
AirComp. That sounds intriguing. Can you unpack that a bit for us?
Sure. So AirComp actually takes advantage of this fundamental property of wireless signals called superposition. So imagine multiple people talking at the same time. Their voices all kind of blend together in the air, right?
Right.
AirComp uses this same principle to allow multiple wireless nodes to transmit their signals simultaneously.
So instead of waiting their turn to speak, they all just chime in at once.
Exactly.
And the receiver can still make sense of it all.
Exactly. And this simultaneous transmission is really crucial because it allows for this decentralized processing, which is incredibly efficient, especially for these large-scale networks. So each node can perform computations independently, just relying on this aggregated signal that it receives from its neighbors without needing this central controller to manage everything.
Okay, so AirGNNs, they combine the power of GNNs with this clever AirComp trick to make things more efficient and decentralized.
Right.
But how do they actually handle that unavoidable fading and noise that's just inherent in wireless communication?
That's a key question, and the researchers tackled it head on. They analyzed the stability of these AirGNNs under various channel conditions using this concept called filter frequency response over the air.
Now, filter frequency response, that might ring a bell for some of our listeners familiar with signal processing, but for those who need a refresher, can you explain it in a way that relates to something we might encounter in everyday life?
Sure. Think about adjusting the equalizer settings on your music player. You can boost the bass, reduce the treble, and so on. That's essentially what a filter does. It shapes the frequency content of a signal.
Okay.
And in the context of AirGNNs, this filter frequency response over the air helps us understand how that combined signal with all its fading and noise is actually processed by the network.
So they're essentially looking at how the AirGNNs filter and interpret the jumbled signals they receive, taking into account the real-world imperfections of the wireless channel. What do they find? Are these AirGNNs as stable as they claim to be?
Well, the results were quite promising. They found that the output variation of AirGNNs remained bounded even when the channel conditions were less than ideal. This means that the network's performance doesn't completely fall apart in the presence of fading and noise.
So they're not bulletproof, but they can certainly take a punch. That's good news for anyone working with real-world wireless systems. But like any engineering solution, I'm guessing there are trade-offs involved, right?
Absolutely. A simpler AirGNN architecture might be more stable, but it might not have that same capacity to extract those complex features from the data.
Yeah.
Conversely, a more complex AirGNN might be better at processing information, but it might also be more sensitive to these channel variations. Finding the right balance for your particular application is key.
So it's that classic balancing act between robustness and complexity.
Exactly. Now let's delve into how these AirGNNs are actually trained. The researchers explored two scenarios, one with channel state information available and one without.
Okay, hold on for a second. CSI. For those of us who might not, live and breathe wireless communication protocols,
Yeah.
what exactly is that?
Great point. So CSI essentially provides information about the quality of the wireless channel between the transmitter and the receiver.
Okay.
Think of it as a measure of how clear and strong that signal is.
Yeah.
So a high CSI means a good connection, while a low CSI indicates a weak or unreliable one.
Okay, that makes sense. So sometimes you have the CSI available and sometimes you don't. What's the difference in how you train an AirGNN in each of those cases?
So when CSI is available, the researchers employed a training procedure called truncated channel inversion power control.
Okay.
It's a mouthful, I know. But it's essentially a strategy for selectively allocating power to different channels based on their quality.
So if you got a strong channel, you give it more power?
Yeah.
And if it's weak, you basically ignore it, kind of like focusing your resources where they'll have the most impact.
Precisely. And this strategy is then incorporated into the training process itself. So the AirGNN learns to adapt to these fluctuating channel conditions by being exposed to different channel realizations during training.
That's clever. It's like giving the AirGNN a crash course in all the possible ways the wireless channel could behave. But what about when you don't have that CSI information? How do you train an AirGNN to handle the unknown?
That's where things get even more interesting. In the absence of CSI, the researchers take a different approach. Instead of trying to predict the unpredictable,
Right.
they kind of embrace the uncertainty.
Embrace the uncertainty. That sounds like a recipe for disaster.
It might seem counterintuitive, but it's actually a very effective strategy. The AirGNN is trained by considering all possible channel conditions.
Wow.
Essentially making it robust to whatever the wireless environment throws at it.
So instead of trying to tailor the training to a specific channel, they just throw everything at it and let it figure it out.
Exactly. It's a more generalized approach that allows the AirGNN to adapt and perform well even when that channel behavior is unknown.
Okay, I'm starting to see the power of this approach. Now, you mentioned earlier that this paper showcased some real-world applications where AirGNNs really shine. Can we dive into those now?
Absolutely. The researchers explored three specific applications: source localization, multi-robot flocking, and wireless channel management. So let's start with source localization.
Source localization.
Yeah.
That's all about figuring out where a signal originated, right?
Yeah.
Like pinpointing the epicenter of an earthquake based on readings from seismic sensors,
Exactly.
or finding the source of a rogue transmission in a wireless network.
Precisely. And in the wireless realm, this is a particularly challenging task because signals can be distorted by fading noise interference. The researchers demonstrated that AirGNNs were able to achieve significantly higher accuracy in source localization compared to traditional methods, especially under these challenging channel conditions.
Okay, so they're essentially able to cut through all that noise and interference to get to the heart of where a signal came from.
Yeah.
That's pretty impressive. What about this multi-robot flocking application? What does that involve?
So multi-robot flocking is all about coordinating the movement of a group of robots to achieve a common goal. Think of a swarm of drones collaborating on a search and rescue mission, or a fleet of autonomous vehicles navigating a busy city.
So it's like a highly choreographed dance. But with robots, I can imagine that communication between those robots is absolutely crucial, especially if they're trying to avoid colliding with each other.
Exactly. And in a wireless environment, maintaining that communication can be tricky.
Right.
That's where AirGNNs come in. They allow the robots to share information about their positions and intentions, enabling them to move smoothly and avoid collisions, even in the presence of these channel disruptions.
So it's like giving each robot a little bit of awareness of its surroundings and the ability to communicate effectively with its neighbors. That sounds incredibly useful for a wide range of applications. What about that last one you mentioned, wireless channel management? What's that all about?
So wireless channel management is all about optimizing the allocation of these wireless resources. Things like bandwidth and frequency to ensure this smooth and efficient communication. It's a bit like air traffic control for data.
I like that analogy.
You want to make sure that all the different transmissions can coexist without interfering with each other.
Okay, so it's about making sure everyone has a clear channel to communicate on and preventing those data collisions. How do AirGNNs help with that?
The researchers show that AirGNNs can be used to dynamically allocate channels to different users or devices, minimizing interference and maximizing the overall capacity of the network. This is particularly important in scenarios with many users competing for limited bandwidth, like a crowded stadium or a busy conference center.
So they're essentially acting as smart traffic cops, directing the flow of data to prevent gridlock. That's a pretty important role, especially as our world becomes increasingly reliant on wireless communication.
Absolutely. And what's particularly impressive is that AirGNNs were able to achieve significant improvements in channel allocation compared to traditional methods, even in dynamic environments where those channel conditions were constantly changing.
These applications are really compelling. It sounds like AirGNNs are a versatile tool for tackling a wide range of problems in wireless communication.
They are. Now, to really appreciate the robustness of these AirGNNs, we need to dig a bit deeper into the analysis that the researchers did on their stability and convergence.
Okay. You've piqued my curiosity. Lead the way.
Oh.
I'm eager to learn more. Okay, let's talk about this stability and convergence. I have to admit, they're not exactly the sexiest topics, but, I know they're crucial when you're talking about deploying machine learning models in the real world.
Yeah.
Especially in, these unpredictable environments like wireless networks.
You're absolutely right. Stability and convergence, they're kind of like the unsung heroes of reliable machine learning. So let's start with stability.
Okay.
In the context of AirGNNs, stability refers to the network's ability to handle these pesky channel impairments.
Right.
The fading, the noise, the interference, without its performance completely falling apart.
Right, we touched on that earlier. You said the researchers found that the output variation of AirGNNs remained bounded even when the channel conditions were rough. But what does that actually mean in practical terms?
Well, think about it this way. Imagine you have an AirGNN that's controlling a swarm of drones.
Okay.
You don't want those drones to start behaving erratically just because the wireless signal gets a bit shaky.
Right.
Stability means that the drones will maintain a certain level of predictable behavior even when the communication isn't perfect.
Okay, that makes sense. You want those drones to keep flying in formation and not suddenly veer off course because of a dropped signal.
Yeah.
So how did the researchers actually measure the stability of AirGNNs?
They used a mathematical tool called the Lifshitz gradient to quantify how sensitive the AirGNN's output is to changes in the wireless channel. Essentially, it measures how much the output can change in response to those fluctuations in fading and noise.
Okay, I'm going to need a little more help with this one Lifshitz gradient. That sounds pretty technical. Can you break it down for us non-mathematicians?
Sure. Imagine you're driving a car up a hill.
Okay.
A steep hill would have a high Lifshitz gradient. A small change in your position on the road leads to a big change in elevation. A gentle slope would have a low Lifshitz gradient. You can drive quite a distance without your altitude changing much. In the context of AirGNNs, a low Lifshitz gradient means the network's output is less sensitive to changes in the channel, indicating greater stability.
Okay, I'm starting to get the picture.
Yeah.
So a low Lifshitz gradient is a good thing. It means the AirGNN can handle those wireless bumps in the road without going haywire.
What did the researchers find in terms of the Lifshitz gradient for AirGNNs?
Well, they found that several factors influence the Lifshitz gradient. As you might expect, a clearer, stronger signal generally leads to a lower Lifshitz gradient and therefore greater stability. They also found that the complexity of the AirGNN architecture plays a role. Simpler architectures tend to have lower Lifshitz gradients.
So again, there's that trade-off between complexity and stability. You might gain robustness by keeping things simple, but you might also sacrifice some processing power. Exactly. It's always about finding the right balance for your specific application. Now let's move on to convergence.
All right, convergence. What does that mean in the context of AirGNNs?
So convergence refers to the process of training the AirGNN. It's about ensuring that the training process leads to a stable and reliable model. Essentially, we want to know that the AirGNN will eventually learn to perform its task effectively given enough time and data.
So it's about making sure the AirGNN doesn't get stuck in a rut during training and actually arrives at a solution that works.
Yeah.
How did the researchers analyze convergence in this case?
Well, they dug into the mathematical foundations of AirGNNs and proved that under certain conditions, the training process does indeed converge. This means that as the AirGNN is fed more and more data, its internal parameters gradually adjust until it reaches a point where further training produces only minimal improvements in performance.
So it's like baking a cake. You keep checking on it, and eventually it reaches a point where it's done, and no amount of additional baking time will make it any better.
Precisely. And this convergence analysis provides a level of assurance that the AirGNN training process is well-behaved and will eventually lead to a reliable model.
That's reassuring to know.
Yeah.
So we've got stability, which means the AirGNN can handle the unpredictability of wireless channels. And we've got convergence, which means the training process is reliable.
Yeah.
It sounds like AirGNNs are shaping up to be a pretty robust solution for a wide range of applications.
They are, and what's particularly exciting is that this research is just the beginning. AirGNNs are a relatively new field with a lot of potential for future exploration.
So where do we go from here? What are some of the big open questions or areas for future research that you're excited about?
One area I'm particularly interested in is developing more efficient training algorithms for AirGNNs. As wireless networks continue to grow in size and complexity, we'll need to find ways to train these models quickly and efficiently. Another area ripe for exploration is security. As we start to rely more heavily on these interconnected wireless systems, ensuring their security will be paramount.
That makes sense. And of course, there's always that quest for better performance, finding ways to squeeze even more out of these AirGNNs and make them even more resilient to the challenges of wireless communication.
Absolutely. This is a dynamic and rapidly evolving field, and I'm incredibly excited to see what innovations emerge in the coming years.
This has been a fascinating deep dive into the world of AirGNNs. I have to admit, I was a bit skeptical at first. Combining graph neural networks with wireless communication sounded like a recipe for complexity overload, but I'm really impressed with how the researchers tackled these challenges head-on, and I'm excited to see what the future holds for this technology.
I share your enthusiasm. AirGNNs represent a significant step forward in our ability to harness the power of machine learning in the wireless domain. They offer a glimpse into a future where wireless networks are not just conduits for data, but intelligent, adaptable systems that can learn and evolve to meet the ever-growing demands of our interconnected world.
To our listeners, we hope this deep dive has sparked your curiosity and given you a new perspective on the possibilities of wireless communication. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of what's possible.